Well, hi there. We're going to have a look at stationary points today, which is a very, very fundamental part of differential calculus. Okay, so without any further ado, let's go. Okay, we've got a question here which says the displacement x meters of a particle moving in a straight line is given by x equals 9t minus a third t cubed. And I kind of think of that as t being seconds. You know, it is seconds, the second line there, where t goes from 0 to 3 root 3 inclusive, and that's the time taken. So find its maximum displacement. Okay, let's do that now. The thing about these stationary points is that if you think about that, if you actually plotted that x versus t function there on the first line, you would find that there would be a maximum point on that graph, and I'm going to show you that in a minute when I'm finished doing the whole thing using calculus. I'm actually going to show you a little sketch of the graph, and you'll see it's got a maximum. And so, but the point to notice is that the gradient where the function has a maximum or a minimum is always 0. The tangent to the curve at a maximum or minimum will be horizontal, which means gradient 0. So that's the whole basis upon which we do these questions. So we're always looking for gradients of these functions equaling 0 if we want to find a stationary point, meaning gradient 0. So let's do it. We've got x is 9t minus 1/3 t cubed. Now we're going to find dx dt because we need the point at which that is 0. So therefore we got that, and we're going to say at maximum x, dx dt equals 0. That is the stationary point. Therefore we say that 9 minus t squared equals 0, and therefore t squared equals 9. Therefore t would be plus or minus 3. Now, we can't have minus 3. Look up at the question and you will see that t has to be positive or 0. Okay, it goes from 0 up to 3 root 3 inclusive. So you can't have that negative value. So reject t is minus 3. Now, here's a little hot tip for you. In any examination situation, if you have to reject one of the solutions because of the context of the question making it unacceptable, you have to actually state that fact and why you're rejecting it, because otherwise they won't give you that. There's always a mark for that, okay? So they won't give you that mark. So just don't go rejecting it with no reason given. You must give the reason. Okay, so t is 3. Hence we're saying that the x maximum, you have to sub that in now because they're actually asking you for the maximum displacement, not just the time. So we sub the time in now, t is 3, and we get 18, and it's meters, okay? Mr. Box, thank you, Mr. Box. And we're going to up and away. Oh, we're going to look at the technology solution now. Yes. How easy is this, guys? Look, what we've done is we've basically defined f1 of x as that thing. I'm using x now, not t, because it's just more convenient on the calculator to use x. And we've done that. Good show. Now we're going to do a solve statement, which is from the algebra menu. I don't even care what the derivative is. I'm just putting it straight into the calculator as solve d by dx of f1 of x is equal to 0, comma x. That means 4x. So the calculator is going to work out the derivative function, the gradient function, and it's going to set it equal to 0, and it's going to solve it for x. Isn't that a clever little calculator? So x is 3 or minus 3. Of course, we rejected the minus 3 because we noticed what the boundary conditions for t were, and in this case x were for this question. So we just then go f1 of 3 and we get 18. Da-da-da-da. Not bad. Now we're going to have a look at the graph. I went over to a graph screen. You get that by doing Control I and selecting graphs. And that f1 of x will already be in the calculator's little brain, and then you get the sketch of it, that's a segment of, and then you just select the graph screen, yes. Then you go Analyze Graph from the menu, and you select Maximum. Then it'll ask you for the lower bound, which is a vertical line to the left of where you want the maximum, and then then it asks you for an upper bound, which is to the right of where you want the maximum, and then it'll just do its little thing, and it'll come up with the maximum point, which was 3 and 18. Clever little calculator, huh? Yeah, it makes you smile all the while on your dial. Okay, now let's do another one. Find the stationary points of the following functions. Well, guys, I can feel some dy dx's happening here, and some dpdt's by the look of it too, and some dpdx's from all these things. Now, it's the same procedure. Now, mind you, we don't know whether these are going to be maxima or minima we're finding, but we do know that they're either maxima or minima that we'll be finding, okay? Because they're stationary points. So, by doing the gradient function, by doing dy dx in this case, we'll find when that equals 0, and therefore the stationary point. So therefore dy dx is da-da-da-da. Yes, do you agree with that? I think so. Now we're going to set that thing equal to 0, okay? And solve it for x. X is 3. That means a stationary point. That means the maximum or minimum of that function, being a quadratic, will occur when x is 3, because that's the point at which the gradient is 0, okay? Yeah, stationary point required, not just the value of x, by the way. Reread the question. So you need the y value as well. So sub x is 3 in, and what do you get? Voila, and you get da-da, 27. So the stationary point is that thing, and you are not finished until you've expressed it in that form. A point means open bracket, the x value, comma, the y value, close the bracket, and then you box it. Hello, Mr. Box. Thank you, Mr. Box. And we're done. That's part A. Let's do part B. What's that one? Oh, that's just P versus T. Now that, guys, is a cubic. So therefore cubics, as you know, they can have a maximum and a minimum, can't they? Depending on what shape they are. Yeah, they can. So let's see what that, but the thing is, I'm noticing that T is greater than 0, so that could be interesting. We might only get one of those because in the region in which T is greater than 0. So let's go for it. Here we go. Let's do a dpdt now. And we got that thing. It's a quadratic, okay? So that might have two solutions, I think. Yes, okay. Let's just set that equal to 0. We get that. Now, oh look, I can spot a common factor. Oh, I love to take out common factors because they make it easier for me to factorise. Now, up and away with Mr. Snail in a minute. Yeah, that's right. Yeah, minus, it's 3t squared. I took out 2, didn't I? Right, divided the whole thing through by 2 to both sides, and I got that. Mr. Snail, are you there? Take us up and away. Ah, thank you. Now, I'm factorising. I've noticed that I can factorise that easily with whole number factors because I took out the common factor. It's not so hard for me to do if I've got smaller numbers to deal with. And I think that's right, isn't it? You better check it. Did I do it right? Yeah, minus 6 from the outside terms, minus 6t from the outside terms, plus t from the inside terms gets me minus 5t for the middle term on the lower left-hand side expression there. Yeah, good, I'm right. So therefore, from the null factor law, I can say that that's the case, or that's the case, can't I? Therefore, t would be minus a third. I can spot a rejection coming a mile off here. Yeah, that's right. So t would be minus a third, or t would be plus 2. But in the context of this question, did you see? Yes, t has to be positive. So no offence, Mr. Minus a third, but we have to get rid of you. Yes. Goodbye, no offence. And therefore t is 2. Okay, so now reread the question. What are we looking for? The stationary point. So we're not finished, are we? We've just got the value of t at which the stationary point occurs. We need the t value and the p value expressed as a point. Yes, so let's go for that. So p at t is 2 is this thing. And it comes to let's clean it up, and we get that. Oh goodness, we just get 1. So when t is 2, p is 1. So there's our answer. and that's not finished until the answer's like that. Thanks, Mr. Box. Good work. Do you see that? The stationary point is that. Don't just say T is 2 and T is 1 and P is 2. That's not right. You've got to put it as a point in brackets. Okay, like that. Okay, next one. Okay, so what do we got? Okay, this is a cubic. So we could have up to 2 stationary points here. A maximum and a minimum for a cubic is possible. Let's see what we get. dy dx is da-da-da-da-da-da. Do you agree? Yep, we're going to set it equal to 0, and we're going to see what we get. Oh, right, I can see. That's interesting. I divided through by 3 and I just rearranged it. So x could be plus or minus 1. That's interesting. So we've got to get the stationary point. So it looks like this thing is going to have a maximum and a minimum because they're not putting any restriction on the domain for this question, like they did for the previous one. So let's just go over the screen and see what we get. That's where we got to. Okay, so therefore, when x is minus 1, we sub in, and we get y would be that thing. Let's clean it up a bit, and we get 2. Well, that's interesting. So therefore, when x is minus 1, y is 2. So the stationary point there would be that one. Right? Let's do the other one now. When x is plus 1, we get that thing there, and oh yeah, that comes to 6. So therefore, the other stationary point is that one, and therefore my answer, just being very super neat and attention to detail, is that, and put a box around it. Thanks, Mr. Box. There's my answer. Okay, so I did have 2 stationary points, yeah? And if you look at that, guys, that's a negative cubic, isn't it? With a minus out the front of the x cubed term. So you visualize in your mind how that's going to look. It's going to come in from the top left. It's going to go zooming down with a minimum. Then it's going to go zooming up and get a max, local max. And then it's going to go zooming out through the lower right-hand side. So I would say the minus 1 and 2, the first stationary point would be a local minimum, and the other one would be a local max. Okay? Sorry about the phone. I'll just get that phone. Wait a minute. Okay, so you got that, haven't you? Let's go with the next one, D. Okay, so therefore we've got P is absolute value of 12x squared minus 6, and we've got to get the stationary point of that. I don't think I can. I just find these things detestably annoying. So I think I'm going to do a graph of it and just work it out without any calculus. Do you mind? I think it's easy. Always go for the easier option unless they specify what they want you to do to find the solution. So here comes a graph. I'm going to do the graph of 12x squared minus 6 in general terms here for a start. All I want is that point, 0 and minus 6. Now, if I modulus that, if I make it the modulus, it means that no y value, or p value in this case, should have had p there on the y-axis, so don't worry, I'm just getting the general shape of it. That means that that bit under the x-axis, below the x-axis, has to go above it, like that. Okay? And I'm going to rub out the bottom section, and that's what the graph's going to look like. So you can see very clearly where the stationary point is, can't you? It's the point with 0 gradient, and it's there at 0 and 6 now. That's x is 0 and p, I meant really, is 6, yeah? Okay, that's it. I didn't do a box around that one, but you get the idea. Okay, last question. Now this is, they've got the curve. It goes through 0 and 5, and it's got a stationary point at 2 and 7. So, look, you've got 3 variables to solve for. So you need 3 equations. Do you think you can scrape up 3 equations out of that? Now have another look at it. Well, it passes through 0 and 5. That's one equation, right? Sub in, x is 0, y is 5. It also passes through 2 and 7, because that's a stationary point, but it's also a point on the curve, isn't it? So therefore we could sub in x is 2 and y is 7, and we'd get another equation, right? But where is the third equation? Well, the clue is you have to use every bit of information they give you in the question. Now, we've used 2 points that are on the curve, but we haven't used That's stationary point information. So that's now it's time to use that. So let's just make a start before I get too ahead of myself. There's the equation. We're going to sub in 0 and 5, okay? And we're going to get that information. Because all the x terms are 0 because x is 0, so we know instantly that c is 5. Very good. Now we're going to sub in 2 and 7, yeah? And we're going to do the same process. A little bit more complicated, but it's going to get us an equation in A and B for you and me. And here it comes. Yes. More simplifying, please, Mr. Computer. It's nice to sit back here and let the computer do it. Yeah, well, that's my equation, isn't it? Lovely. 2a plus b is minus 3. And I looked for the common factor, didn't I? Yes, I did. Always look for that common factor. Now, what are we going to do now? As I said earlier, we've now made a lot of progress. We've got c sorted out. We've got an equation in a and b, the remaining two variables. But I've got to use another clue somewhere. And the information that I have not used in that question is about the stationary point. So the stationary point occurs when the gradient is 0. So let's find the gradient function and put that point, x is 2, but the gradient is 0 at that point. That's what we do. So dy dx is 3x squared. Just took the gradient of that function y, and I got that. Agree? Good. Now, what we're going to do is we're going to say x is what? 2, and dy dx is 0. That's right. That's right. Into that equation, right? Thank you, Mr. Computer. Clean it up a bit for us. It's lovely being telling the computer what to do, isn't it? Now, I think we're going to write another line there, fix it all up. Now, there's my second equation in A and B, and I'm going to solve them simultaneously. I think Mr. Snail's going to take us up and away. Thank you, Mr. Snail. And we're going to, I worked out what to do. I'm going to subtract 2 from 1, okay? 2 from 1. Now, be jolly careful when you're subtracting. You don't mess up all the signs. So that means we're taking 4a away from 2a, and we get that, and therefore, oh goodness, I was fast, wasn't it? And we're taking b away from b, getting nothing, and we're taking negative 12 away from negative 3, so that's minus 3 minus 12, which gets us plus 12 and gets us plus 9. Solve it for a, minus 4.5. Jolly good. Now we're going to substitute a as minus 4.5 into 1, and that's there. The red arrow points the way to equation 1. By the way, please document your steps when you're doing simultaneous equations. Don't give us the no documented gobbledygook version. It drives us all crazy, and it helps us a lot when we can see the logic that you're following, okay? Okay, so let's do that. We'll substitute a as minus 4.5 into that equation. So what do we get? 2 times minus 4.5 plus b is minus 3. Cleaning up, we get minus 9 plus b is minus 3, and therefore b is minus 3 plus 9, adding 9 to both sides, and we get therefore b is plus 6. Wowee! I think we've done it, haven't we? So we had to specify the values of a, b, and c, rereading the question again. So here we go. The final finale line. There it is, and a box. Thank you, Mr. Box. Now, come with me over the screen, guys, and I'll show you the incredibly easy technological way of doing this. It'll just knock your socks off. Let's go. There it is. Okay, now, let's just go through it step by step. What did I do? In 2 lines. I did that in 2 lines. I put that in. I put x cubed plus ax squared plus bx plus c equals, I put it in as f1 of x, function 1 of x, making jolly sure I had not some previously defined values for a, b or c, making sure they're not already stored as some value as a memory variable. I did that. That's beautiful. And then now just check this out. Check this second line out. This is the beauty of the calculator. I've just simply said solve for, okay, f1 of 0 equals 5. That means x is 0, y is 5. That'll be an equation in A, B and C, won't it? Secondly, I'll put in there f1 of 2 equals 7. That's the second point they gave us on the curve. And thirdly, now check this out, that the derivative d by dx of f1 of x equals 0, and that little vertical line after the 0 means with x equals 2. That's the way you have to express that. You can't just put in d by dx of f1 of 2 equals 0. The computer will freak out. You can't do that. You have to say f1 of x equals 0, so it can work out the derivative of f1 of x, then equate it equal to 0, and then set x equal to 2. That's what it has to do. That's what you have to do to help it work out what it's doing. Then you put, after those three equations there, you put comma A, comma B, comma C. That's what you're solving for. And look what you get. It just spits them out. There they go. It just spits that out. A is minus 9 over 2, B is 6, and C is 5. It's rather neat, isn't it? Yeah? So that is it, guys. So please practice that. Practice doing that on the calculator. You need to get very good at being able to use the calculator. Now, who have we got to talk to us? Hello, Mr. Star. What do you think? Yes, Mr. Star is one of us, guys. He's got the bug. He loves calculus. Now, I know you love calculus too, don't you? Of course you do. And so do I. So thank you for listening to my little presentation, and I'm going to have a cup of tea, and I suggest you too. You do too. So I'll see you later. Bye.